Okay, so let's begin as usual. Are there any questions? Homework 2 is due today, right? So when you have it, hand it up here. The last thing we were talking about was renewal theory, and that was the stuff that begins on page 200. And what we had was this. We have a process in which there are events which I'll indicate by arrows. And the times between arrows are independent, identically distributed. So let's call those times x1, x2, and so forth. And the distribution function of the x's, the probability that any x is less than or equal to t, is called, what do we call it, f or g? I guess we called it g. And furthermore, the expected value of the x's is equal to beta. And the idea is that you imagine this process going on, and then there's some other point, let's call it capital T, at which you make an observation. And that point is selected without knowledge of the underlying renewal process. And so when you do that, you break apart. You interrupt one of these intervals. And the interval that you interrupt, you'll call I. Of course, the I is one of the x's. And then there's the time from the interruption until the next renewal, and that's called the forward recurrence time. We'll call that R. And then we have the backward recurrence time, or the age of the interval, which we'll call A. And of course, A, R, and I depend on T. But we'll be concerned with a limiting case where T goes to infinity, which means that for all practical purposes that the origin is an infinite distance away, so that there's no boundary effect. And then we're concerned with the equilibrium distribution of R, A, and I. Of course, A and R have the same distribution by symmetry, although they're in general not independent of each other. All right, so we had already derived some results about that, and I'll get to those as I need them. Now, suppose that we ask for the limit as t goes to infinity. Here I'm going to use little t because I'm talking about the mathematics. Maybe I should have called it a little t here. Okay, so this is going to be a sub t, r sub t, I sub t. I want to get the limit as t goes to infinity of the probability that r sub t is less than or equal to little x. And let me just call that capital F of x. And then what I want to show is this. Here's my theorem. My theorem is that capital F of x is equal to 1 over beta integral from 0 to x of 1 minus g of c dc. All right, so I want to prove this, and I want to prove some other things from it. For example, if I have this, then the expected value of this thing, that is the integral from 0 to infinity of x df of x. That would be the expected value of the random variable's distribution function of that. That turns out to be equal to beta over 2 times 1 plus sigma squared. I think I'll write it as the variance. One plus the variance of the interrenewal intervals divided by the expected value squared. And another way to write that is that's the same thing as the variance divided by 2 times the mean. Excuse me, it shouldn't be the variance here. This term should be the expected value of the square of x, the second moment. Now, in the particular case in which x is exponentially distributed, then it's easy to show that the variance is equal to the mean square. That's always true for an exponential, so that this ratio becomes 1. The multiplying factor becomes 2. That cancels with that 2. And you find out that the expected value of the forward recurrence time in equilibrium, actually equilibrium is necessary in the exponential case, is equal to beta, or in other words, is equal to the expected value of the length of the interval, which means that of the original interval, x, which means that the average value of the covering interval is twice the average value of an ordinary interval. And that's sort of a paradox, which we discussed already. Also, if I assume that the x's are exponential and plug in the distribution function for the exponential here and evaluate this integral, I will get exactly the same exponential back. So this is consistent with what we already know from the Markov property. Okay, so the first thing I want to do is let me assume that this is true before I prove it, and I want to calculate its Laplace-Dieltrich transform because that's of some interest, and then from that I want to calculate the expected value. Actually, I'll leave that part as an exercise. Okay, so what I want to do is I want to calculate phi of s, which by definition is the Laplace-Dieltrich transform of this thing right here. So that would be the integral from 0 to infinity of e to the minus sx df of x. That's the definition. So now I just want to do some arithmetic because this turns out to be characteristic kind of arithmetic that we do for problems of this type. Okay, so what I do is I replace f right here by this thing right here. So then I would get the integral from 0 to infinity of e to the minus sx. Okay, now if I take the derivative of a function, here's the function, and I'm differentiating this, which is an integral with respect to the upper limit, then what happens is, in effect, the differential operator cancels the integration operator, and the upper limit comes down into the integrand. This is a special case of Leibniz theorem. Okay, so this is, now, this of course is the well-known stuff from ordinary calculus. All I'm claiming here is that if I have Riemann-Stieltjes integrals instead of ordinary Riemann integrals, everything is the same, except that I talk about d instead of the derivative, the differential instead of the derivative. So in other words, I take the differential of this, which is simply the integrand with the dummy variable replaced by x. So that means that this thing will then turn out to be 1 minus g of x dx with the beta taken outside. Okay, so now I'm just working from the definition. Now comes the tricky part. Of course, it's tricky only the first time you see it, which is ordinarily what you try and do to evaluate things is you try and make them smaller in a sense. But I'm going to evaluate this by making it bigger by replacing this piece by its integral representation, then interchanging the order of integration, and then everything pops out. Okay, so what I'm left with then is this. Now let's see. That's the integral. That's 1 over beta, integral, 0 to infinity, e to the minus sx. And then I notice that if g is the distribution function of a random variable, then 1 minus g is the probability that that is greater than x. So in other words, this piece right here would be replaced by the integral of dg of y, say, as y varies from x to infinity, and then we have the dx. Okay, so this piece right here is the same as that. Okay, it's the probability that the random variable whose distribution function of g is g takes a value greater than x. Okay, now comes a little trick. Now what I want to do is I want to integrate this thing, and so what this says is that I'm going to integrate over y, and I'm going to integrate over x. So let me call this y, and let me call this x, and here's the line y equals x. And what you see here is that as I'm integrating, what I'm going to do is I'm going to fix the value of x, and then I'm going to let y vary from x to infinity. So I fix a value x, and then I let y vary from x to infinity. So that's for a particular x, but x is going to run from 0 to infinity. So that means that I'm going to be integrating over this triangle in these strips like that. So this would be for a smaller x, and the next x, and the next x, and so forth. So what I'm going to do is I'm going to replace that. I'm going to interchange the order of integration so that instead of integrating over by fixing x first I'll fix y, and I want to integrate over the same range. So that means that if I had a y fixed, for example, I would integrate as y runs from 0 to x, and then the y is going to range from 0 to infinity. So I would be integrating over these horizontal strips instead of over the vertical strips. Of course, from a mathematical point of view, you have to prove that you can interchange the order of integration and everything is still okay, but that's standard stuff from analysis. And it always works with well-behaved functions, which of course is what these are. So that's going to give me this. I'm going to get 1 over beta integral. So I've got 2 integrals now, and now the let's see, what I'm going to have now is e to the minus sx, that's this piece. Then I've interchanged the order of integration, so this is dx, and here's dg of y. And on the outside, the y is ranging from 0 to infinity. And on the inside, the x is ranging from 0 to y. Okay, now this piece is easy. It's an ordinary Riemann integral. And in fact, this is an exponential. So if there were an s here, this would be the integral of the density function of an exponential with parameter s from 0 to y, which would be the probability that that the random variable would be less than y. So that integral is equal to 1 minus e to the minus lambda y divided by s. That's the integral. Then I have my 1 over beta integral from 0 to infinity dg of y. Okay, then I take the s outside. So what I'm going to get here is 1 over beta, and then I've got my s. Okay, now what I'm integrating is 1 minus e to the minus lambda y from 0 to infinity with respect to y. So the first term, the 1, is just integrating this distribution function over the whole range of definition from 0 to infinity, so its value is 1. And the second piece is simply the integral of e to the minus lambda y dg of y, which by definition is a Laplace-Dieltjes transform of the distribution function g of y evaluated at, see, I shouldn't have an s here, a lambda, I should have an s. Let me erase this. Okay, let me repeat that because I screwed it up. Okay, but if I integrate that, I'm going to get the Laplace-Dieltjes transform of this, which I will call gamma of s. Okay, so what I did was I started out and I wrote the definition. Then I took the value of f, which I know, although I haven't proved this yet. But when we do, we will have this result. And I plugged it into here. Then I interchanged then I recognized that this thing could be written as an integral. And the trick there is to do that to get a double integral and then to interchange the order of integration. So instead of integrating over these vertical strips, I integrate over the horizontal strips. And that gives me something in which I can evaluate the inside integral. And when I evaluate this integral, I get this piece right here. And then I recognize that this piece just gives me 1. And this piece, in fact, is the Laplace-Dieltjes transform of that evaluated at s. And that gives me this result. So the conclusion is as follows. If f is given by this, then the transform of f, if I call that phi, is given by the right-hand side, in which gamma is the transform of g. Okay, so this is our result. And this will turn out to be important later on in the course. We're going to use that result. Okay, so this and this are equivalent. Okay, now it's a simple matter to differentiate this. I can differentiate this since that s equal to 0, and that will in fact give me my expected value. So this thing right here is, of course, minus the derivative evaluated s equals 0. So I'm not going to do the arithmetic, but that's what it'll come out to be. Okay, so this now should be stored in your repertoire of results, as well as this method. And so should this result here be stored in your repertoire of results. And what we have to do now is I have to prove that, in fact, this statement is true. That is, I'm going to write, now I'm going to go through a mathematical analysis to calculate this probability here and take this limit. And then we'll be ready to go into queuing theory. Okay, any questions so far? Okay, let me erase this. Okay, so what I'm going to do is I want to write an expression for the probability that r sub t, I'll draw a picture in a minute, is less than or equal to x. And then take that limit as t goes, take a limit of what I get as t goes to infinity. Okay, so first of all, let me redraw the picture here. Okay, let's suppose that here's 0 and here's t. Now, r sub t is the time from t to the next renewal. And we want that time to be less than or equal to x. So let me write, say, t plus x right here. Now, if the time to the next renewal is less than or equal to x, that means that there must be at least one renewal between t and t plus x. So there's one, and so forth. And then, of course, there's got to be the next one after time t plus x. Okay, so let's call this last one here. Let's say that that occurs at time y. And let's say that that is the jth renewal, which means that that is the jth plus first renewal. Okay, so here's the formulation. Here's some point t, and we're going to measure r sub t as the time from t until the next renewal, which in this picture would be this. And if we want r sub t to be less than or equal to x, then if this is t, then between t and t plus x, there must be at least one of these arrows, one of these renewals. So let's call tj the last one of those that occurs prior to time t plus x, which means that tj plus 1 is the first one that occurs after time t plus x. And then what I'll do is I'll simply add up the probability associated with this over every possible j. So in other words, r sub t could be less than or equal to x if the first renewal is the one that occurs right here, or the second, or the third, or the fourth, and so forth. Okay, so what I got to do is I got to write all that stuff down. Okay, so here's the probability that r sub t is less than or equal to x. Again, tricky probability argument, just like this is a tricky argument here. But these are just little tricks that there's only a small number of them, and after you've digested them, then you got the idea and you can apply these things later. Okay, so let's see. First of all, let's calculate the probability that the jth renewal in fact occurs at time y. So that would be the probability that t sub j is less than or equal to y, the differential of that. Okay, that's because, remember that the probability that t sub j is less than or equal to y is in fact the distribution function of t sub j evaluated at y. So if I take its differential, that's like the density function dy. So this is the probability that the jth renewal occurs at time y, or in an infinitesimal interval about time y. Okay, now, if the jth renewal occurs at time y, and if it's to be the last one, then the next one must occur after time t plus x. And since the interrenewal times are independent and identically distributed and have distribution function g, therefore that probability is 1 minus g of t plus x minus y. Okay, so this is the probability that the jth renewal occurs at y, and then this is the probability that the next renewal measured from y is greater than t plus x minus y. Okay, if that's t plus x and that's y, then this distance here is t plus x minus y. So then this is the probability that the jth renewal occurs at y and the jth plus first renewal occurs after t plus x. Okay, so now we want to calculate the probability that r sub t is less than or equal to x, and we've calculated the probability that the jth renewal is the last renewal to occur before time t plus x, and we know that r sub t will be less than or equal to x if and only if at least one of these renewals occurs between t and t plus x. And if at least one occurs, then there's the last one, and the last one could either be the first one in the process, or the second, or the third, and so forth. So now what I have to do is I have to add that up over all values of j from 1 to infinity. But also remember that I have to integrate this over all values of t sub j, all values of y, that lie between t and t plus x. Okay, that looks complicated, but let me go through the reasoning again. After you think about it a while, a couple of years, makes perfect sense. All right, I want to get the probability that r sub t, which is the time measured from t to the next renewal, is less than or equal to x. So I take my value t, and then I add on to that a value x, so I have an interval between t and t plus x. And then I say that the time from t to the next renewal will be less than or equal to x if there is at least one renewal between t and t plus x. And if there's at least one, then there has to be a last one. So let the last one be the jth one, which means if it is the last one, that the next one, the jth plus first one, occurs after time t plus x. So first, I fix the probability that the jth one occurs exactly at y, and then I multiply that by the probability that the interval that begins at time y is long enough to cover t plus x, which means it's greater than t plus x minus y. And then I add up all values of y as they ranges from t to t plus x, and then I sum over all possible values of j from the first renewal in the process to the second, the third, the fourth, and so forth. So now I've taken into account everything, and I've done it in a way that I haven't biased anything. That's the trick here, is I want to make sure that I'm not making any assumptions about the distribution of the length of the interval that covers a certain point as being the same as all the others. Okay, so I've taken everything into account without making a mistake as far as I know. Okay, so this is just a straightforward, standard, applied probability stochastic processes type argument. Okay, the next thing now we just start doing some manipulation. The obvious thing is to bring the summation sign in here. So now I'm going to write that as a differential I don't know if it's obvious, but it's certainly obvious after you see it. So as usual, what you do with these things is you write something down and then you change it around so you can make a calculation. However it is, the calculation is made some other way. If you write it AB, then of course you have to make it BA in order to make the calculation. Okay, so I bring the summation sign in here, and then I recognize that TJ is the same as SJ. We talked about this earlier when we first started talking about renewal processes. But here I want to emphasize that TJ, which is the time of the jth arrival, is the sum of the first j inter-renewal times, or inter-arrival times. Okay, so I'm going to take advantage now of that particular interpretation. So all I did was recognize that TJ and SJ are the same thing, and I took this sum and I put it right in here, right there. Okay, then I'm left with the rest of it still the same. 1 minus g t plus x minus y. And then I have the integral from t to t plus x. Okay, now the next thing is to recognize that from 7.5, which we derived earlier last time, that thing right there can be replaced by m of y. So this is by 7.5. Because we proved in class that this sum, if we wrote it out term by term, was the same thing as the definition of m of y, which is the expected value of the number of renewals that occurs in time y. Okay, so that means, let me get rid of this statement here. That means that where it stands now is that the probability that the forward recurrence time is less than or equal to x is the integral from t to t plus x of 1 minus g of t plus x minus y dm of y, where g is the distribution function of the times between renewals, the inter-renewal intervals, and m of y is the expected number of renewals in an interval of length y. Okay, now I'm going to appeal to a result, which is a famous result. So by appealing to this theorem, in a sense, I don't have to prove what I'm going to write down. I can simply refer you to books on renewal theory where you look up the key renewal theorem. Obviously, from its name, it's a key theorem. But actually, the proof of it, although it's mathematically subtle, mathematically sophisticated, from an intuitive point of view, it's almost obvious. So let me write down what it is and then explain to you why it ought to be what it is. Okay, so here is the key renewal theorem. The key renewal theorem says that if I took the limit as t goes to infinity of that right-hand side of the integral between t and t plus x of 1 minus g of t plus x minus y dm of y, that what I would get would be 1 over beta times the integral from 0 to x of 1 minus g of c dc. Which of course is what we want to prove, because we want to prove that the limit of this probability as t goes to infinity is given by this result right here. So what I have to show, what the key renewal theorem says, is that if I take this thing, which was obtained by a strictly probabilistic argument, and I now apply some theorem from analysis which says, well, if I take this limit, it will give me this result, then I've got my theorem. Okay, so what I have to do is I have to argue why it should be true that if I take the limit of that thing, it turns out to be that. Okay, so I think what I'll do is I will erase this piece right here. And I'm going to argue intuitively for why that should be true. Okay, now, the heuristic argument is this. Notice that what we're doing up here is we are letting t go to infinity. So if you let t go to infinity, then in effect you are taking this origin and you're pulling it farther and farther away. Now the value y ranges between t and t plus x. So as t goes to infinity, that value goes to infinity and that value goes to infinity, but the window, the length of that window remains constant. It's x. So I'm just taking this window and I'm moving it along here. And so by doing that, the length of the window remains constant, but the y value is going to go to infinity. Because as t goes to infinity, as I move the window farther and farther to infinity, the y value, which lies inside that window, must go to infinity. So as y goes to infinity, then what happens to this thing m of y? M of y, remember, was the expected number of renewals in an interval of length y. And we had the so-called elementary renewal theorem, which said that, let's see, it said that, that m of y, the average number of renewals divided by the length of time, was roughly the average time between renewals. I got that backwards. Let me say that again. If I take the length of time, wait a minute, let's see, I'm looking at equation, yeah, which says that the average number of renewals, yeah, I had it right, divided by the length of time is equal to y over beta, average number of renewals. Here we go. Why am I getting confused on this? The average number of renewals in time y is roughly the length of time divided by the average time between renewals. So as t goes to infinity, y goes to infinity, so m of y is asymptotic to y divided by beta. Okay, so that being the case, what I do is I replace m of y by y over beta. Okay, so now we're going to get this. We're going to find that this integral right here approaches the integral. In fact, I think I'll write it this way. Intuitively, we could say that this is going to be equal to, well, we want the limit, so I'm going to write it as approaches. So as y goes to infinity, this integral is going to approach the integral from t to t plus x of 1 minus g of t plus x minus y. And in place of dm of y, I'm going to write dm of y is equal to dy over beta. So here's my dy, and here's my 1 over beta. Now, of course, the intuitive part here, the reason this isn't precise is because the t that's going to go to infinity also fits here, here, and here. But the intuitive argument is that the only thing that's going to affect this part is not the value of t, but the length of the width of this window. So as I let t go to infinity, all that happens is the t plus x minus y and the width of that interval, which is as y varies from t to t plus x, that is not affected. So first I'm going to then separately take the limit as the y part goes to infinity, which is the part that's sitting right here. That part we identified as m of y, and we know that as y goes to infinity, m of y, being the average number of renewals in time y, is roughly equal to y divided by the time between renewals. Okay, so I make that step, and now the rest is simple. Okay, so now I will make the substitution t plus x minus y equals c. So this is going to give me 1 over beta integral of 1 minus g of c. Okay, now if t plus x minus y equals c, then when I differentiate, when I calculate dy, I'm going to get dy is equal to minus dc. So that's going to give me a minus sign here and a dz there. Okay, now when y is equal to t, then t plus x minus y is equal to c. And when y is equal to t plus x, then t plus x minus y is equal to 0. And then I recognize that instead of integrating from c to 0 with a minus sign, I can in effect cancel those out, and so I multiply it by plus and change the order of integration, the order in which c travels. So I make it go from, this should be an x by the way, I make it go from 0 to x instead of from x to 0. And now I've proved the theorem. Okay, so the key renewal theorem has to do with this limit, whether or not this limit is equal to that. And what I've argued here is that by ordinary probabilistic arguments, the distribution function I'm looking for is given by this, and then I make this intuitive argument to actually take the limit, which says that as t goes to infinity, in effect all I'm doing is taking this window of fixed length x and moving it farther and farther away from the origin. And therefore the y, which is trapped between the t and the t plus x, must be going to infinity. And that allows me to replace the m of y by y over beta, and then everything else is just ordinary arithmetic. Okay, so in that sense, we don't really need to prove the key renewal theorem unless you're interested in the mathematics for its own sake, because this is exactly the result that you would expect to get. Okay, so now we know that this is true. That is that the limit of the probability that r sub t is less than or equal to x as t goes to infinity is given by this integral. And if we take the Laplace-Dirichlet transform of that and call it phi, then we get this result right here. So this relates phi to gamma. So it gives us an equilibrium for a renewal process in equilibrium interrupted at random. We have the Laplace-Dirichlet transform of the distribution function of the remaining time from the interruption until the next renewal in terms of the Laplace-Dirichlet transform of the distribution function of the original time between renewals. And of course, if we chose the interrenewal times to be exponential and evaluated this gamma, then it would turn out that when you plugged into the right-hand side, this is another exercise, the phi would also turn out to be the Laplace-Dirichlet transform of the exponential. That's, of course, the Markov property. The exponential reproduces itself here, but no other distribution does. Okay, so that's our renewal theory. Any questions about that? Can I go over the probabilistic argument or the interpretation? Okay, this is classical applied probability theory, I think. Okay? We're going to use these theorems, but you have to understand what they mean, but it's not important to us to prove the theorems, not important for this particular course. What is important is the original probabilistic representation, the understanding of why that the mathematical theorem should be true, and what this really means. And what it really means is that if I have this renewal process and I interrupt it at random, then I have the relationship between the length of the interrupted intervals, or the remainder of the interrupted interval, and the length of an ordinary interval. Okay, so now I want to apply all this to derive what you might argue is the most important single formula in queuing theory, the PolyCheck Engine formula. Now when I do that, the derivation, I'm going to get this two ways. The first derivation is going to use this stuff, and it's going to be completely intuitive, but I think very useful and insightful. And then we'll do a complete analysis in which we get the total distribution and calculate things by arithmetic using what's called the embedded Markov chain analysis. Okay, so here is my PolyCheck Engine formula for MG1. PolyCheck Engine. That's P-O-L-L-A-C-Z-E-K K-H-I-N-T-C-H-I-N-E. At least that's one spelling of it. Okay, PolyCheck published a paper in which he derived this in 1930 and Kinchin independently in 1932. And you could probably view these results as being the first mathematical results in queuing theory after Erlang's original sort of non-mathematical work. And what the PolyCheck Engine formula says is the following. The expected value of the waiting time is equal to rho times tau divided by 2 times 1 minus rho times 1 plus sigma squared over tau squared. Where? Well, I got to define what these things are. Tau is the expected value of x. So x are the service times. So by definition, tau is the expected value of x, and sigma squared is equal to the variance of x. And rho, by definition, is lambda times tau, where lambda is the arrival rate. And of course, you recognize this is equal to the offered load. And since this is a delay model, this is also equal to the carried load. And of course, that means this thing must be less than 1. This can be written as rho over 1 minus rho. And then you have tau over 2 plus sigma squared over 2 tau. And you recognize this as being somehow or other related to renewal theory. Because what it says is, suppose I had a renewal process in which the times between renewals were the service times. Okay, so I'm going to have the arrows pointing down because those things really represent service completions. And then suppose that I interrupted one of these renewals, one of these service times. Then the remaining service time would be equal to the average service time over 2 plus the variance of the service time divided by 2 times the average. Let's see, this should be, that's right. Okay, so this is the renewal theory result right here. So the average waiting time is a multiple of the remaining interrupted service time. And that multiple is rho over 1 minus rho, where rho itself is the server utilization. So this is really very simple when you make this, when you interpret the terms this way. But then the question is, why should this be true? It turns out that it's rather complicated to derive this. I'm going to start out by deriving it in a intuitive probabilistic argument using the renewal theory result. And then we'll derive it directly in a more rigorous way without assuming anything, no renewal theory, and then this will drop out without making any assumptions. But it's worthwhile doing it, making the intuitive assumptions, because that gives understanding as to what's going on. Okay, so I'll start off with equation 8.2. So what I want to do is I want to derive this result, this famous PolyCheck Engine formula. By the way, notice that the PolyCheck Engine formula shows that the average waiting time depends on the server utilization, the average service time, but it also depends on the variance of the service times. Up to this point, we've always had the case where everything is exponential, so the variance of the service times doesn't explicitly come in there. And every result we've got either applies only for the exponential or applies for every case, and that is insensitive. But now for the first time, we have formulas which apply for a case in which the service times are not exponential, and it matters that they're not exponential. Okay, so now I want to derive this result using this intuitive argument. Because remember that the whole point of this course is to understand what's going on rather than just state formulas. And I think this helps. So I'm going to start off with equation A2, a general equation for the expected value of the waiting time. So you could always say, using the definition of conditional expectation, that the expected value of the waiting time is equal to the expected value of the waiting time given that the waiting time is greater than 0 times the probability that the waiting time is greater than 0 plus the expected value of the waiting time given that the waiting time equals 0 times the probability that the waiting time equals 0. We don't have to worry about negative values because you can't have a negative waiting time. However, we don't have to worry about this term, the second term either, because obviously the expected value of the waiting time given the condition that the waiting time is 0 must be 0. Okay, so what I got to do is I've got to somehow or other evaluate these terms and be able to solve for E of W to give me this result right here. And we know that somehow or other renewal theory is going to come into it because that's the answer. Of course, that's sort of with hindsight, but you could have gone through this argument originally without knowing anything, without doing anything the way PolyCheck and Engine did. Okay, so first of all, to do that, I'm going to define a new random variable z, which is either 0 or 1. It's 0 if the server is idle, and it's 1 if the server is busy. And so z then is equal to the number in the server. Okay, one of the things I'm going to use here is Little's theorem, in which the server is the system. And in that system, there can be I can be either state 0, which means nobody's in it, or 1, which means somebody's in it. Okay, so all kinds of things are going to come together here now. Little's theorem, pasta, and renewal theory. All right, now, we have this z, so let me calculate the expected value of z. Now, any random variable z that only takes the values 0 and 1, a so-called 0, 1 random variable, has as its expected value the probability that z equals 1. That is, the expected value of z is 0 times the probability z equals 0 plus 1 times the probability z equals 1. That's true for any 0, 1 random variable. But what is the probability that z equals 1? Well, that's the probability, that is, the probability that the number in the server is 1 is equal to the probability that the number in the system is either 1 or 2 or 3, what we've called capital Pj, P1 plus P2 plus P3 and so forth. Okay, so the expected value of z is equal to the probability that the server is busy, which is equal to the sum of the state probabilities for the MG1Q, summed from j equals 1 to infinity. Now, what's the probability that W, the waiting time, is greater than 0? That's this piece right here that I want to get. And I say, well, that probability is equal to the probability that the arriving customer finds the system in state 1 or state 2, and so forth. So the probability that a customer has to wait is the probability that when he arrives, he finds the arriving customer's distribution. He finds the system in state 1 or state 2 or state 3 or so forth. And of course, that is equal to this by pasta. Okay, so the probability that the customer has to wait at all is the sum of the probabilities from the viewpoint of the outside observer, the sum of the state probabilities. Okay, but what about this thing here? Now, we know that these things are equal to this expected value. So therefore, since those things are equal to that expected value is the expected value of the number in the server. So I have a system now which consists of the server. And I have customers arriving and entering the server at rate lambda. Now, they don't necessarily enter the server immediately at rate lambda because sometimes when they arrive they have to wait in a queue. But nevertheless, if I look at the picture, I have customers arriving, queuing up, and then I have the server. So I'm going to define my system as being the server. So from the viewpoint of Little's theorem, I can view the server as the system and say that L equals lambda W, which means that the average number in the server is equal to lambda times the average time in server. Okay, now the average number in server is the expected value of Z, and the expected value of Z is the sum of those probabilities, and that is this thing right here. Okay, so what that means then is that by Little's theorem, the sum of those probabilities, which is this thing right here, is equal to the lambda, the rate of entry into the server, times the average time spent in the server. But the average time spent in the server is the average service time, so that's lambda times tau. So this equal sign follows by Little's theorem. Okay, so look how all of these things tie together now. We want to calculate the probability that the waiting time is greater than 0. And that is the sum of the probabilities that the arriving customer finds a system in each particular state. But the probabilities from the viewpoint of the arriving customers are the same as the probabilities from the viewpoint of the outside observer by pasta. And those probabilities are the same thing as the expected value of Z, the number of customers present in the server, because that's a 0-1 random variable. And since that's an expected value, then by Little's theorem, that expected value, if I look at the, if the Z describes the state of the server, is the rate of entry into the server times the average time spent in the server. And so therefore, the fraction of customers who have to wait at all is equal to the arrival rate times the average service time. Okay, so we got that. Now let's go to equation 8.3. 8.3 is simply a rewrite of 8.2. It says that the expected value of the waiting time is equal to the expected value of the waiting time given that the waiting time is greater than 0 times the probability that the waiting time is greater than 0, which we already know is lambda times tau. Okay, now let's look at this piece right here. Here I have an arrival rate, a lambda, times an average time. So again, I'm going to apply Little's theorem by saying, well, what is this? This is the expected time given that the waiting time is greater than 0. Okay, so the waiting time is the time that you spend in the queue. So now I'm going to use Little's theorem in which the system is the queue. And I'm going to look at the queue only. I'm going to look at only those arrivals that, shouldn't say it that way, let me say it another way. I'm going to look at the queue only during the times that the server here is busy. Waiting time is greater than 0. Now, the W is the time spent in the queue, and what we've called capital Q is the length of the queue. So we've argued previously that the arrival rate times the average time spent in the queue is equal to the average length of the queue. So now I'm going to apply that exact same argument, except that I'm carrying along the condition that W is greater than 0. So that means that I'm going to replace this piece here by the expected value of the queue length given W is greater than 0. Okay, so this is true by Little's theorem again. And here's my tau. Okay, so the expected value of the waiting time is equal to the expected value of the queue length given that the waiting time is greater than 0 times the average service time. And this expected queue length greater than 0 is, in Little's theorem, that's the L, that's the W, and that's the lambda. Okay, so average queue length given this condition is equal to entry rate into the queue times average time in queue given the same condition. So the only thing that I'm doing here that's a little bit flaky with regard to Little's theorem, as we've used it before, is that now I'm carrying along this condition. But intuitively, that really shouldn't make any difference because all that says is I'm just restricting the time I'm looking at it, but I'm restricting it the same way here as I am here, so I should get the same result, same relationship. Okay so far? Okay, now let's look at this W. The W, which is the waiting time, is equal to, well, when the customer arrives, he finds a certain queue length. And so his waiting time is the sum of the waiting times of all the people that he finds in the queue, plus the partial, excuse me, I said waiting times. The waiting time of the customer is the sum of the service times of all the customers he finds in the queue, plus the partial service time that he interrupts, the remaining service time of the interrupted service time. So in other words, the waiting time is equal to the service time of the first person in the queue plus the service time of the second person in the queue, and so forth, up to the service time of the last person in the queue. In other words, it's the number of service times there are, one service time for each member of the queue, plus the remainder, that's where the renewal theory is going to come in, plus the remainder of whoever is in service at the time the customer arrives. We know that there is such a person because we're going to calculate this conditioned on W greater than 0. Okay, now equation 8.5 says the following. We want to calculate expected values here, and I want to calculate expected values given this condition. In other words, I'm trying to calculate that thing right there. Okay, so now I say that the expected value of the waiting time, given that the waiting time is greater than 0, is equal to the expected value of this stuff here. So it's the expected value of x1 up through xq, given that W is greater than 0, plus the expected value of R, given W is greater than 0. That's this R right there. So the expected value, if I take the condition that W is greater than 0, the expected value of the waiting time, given that condition, is the expected value of this stuff, given that condition. And that can be broken down into two terms, the expected value of the sum of those Q random variables, plus the expected value of the remainder of the interrupted service time. Remember, this is kind of a confusing argument, but the arguments are all probabilistic now. Okay, now, what about this piece right here? Now we have, this is a compound sum. Because what I have here is I have the expected value of a sum of random variables, but the number of terms in the sum is itself a random variable. And we proved on exercise 5, which is on page 199, that the expected value of a random sum of random variables is equal to, as you might expect, the expected value of the individual components multiplied by the expected value of the number of components that there actually are in the sum. Okay, so by exercise 5, page 199, this thing here becomes the expected value of the queue length, that's this piece, given the condition that W is greater than 0, times the expected value of the x inside that sum, which is E of x. They're all the same. Okay, so let me go back up here now and call this H6. The equation numbers that I'm writing here are key to the numbers in the textbook. But the argument is a little bit more detailed than what's in the textbook.
I have a
Question?
waiting time. W equals to x1 plus xq plus r.
Okay. Here's my queue. There's the server. There are the customers waiting in the queue. And here's the test customer. Now, when he arrives, what he finds is in front of him, he finds some number q. That's the length of the queue. So his waiting time is the amount of service that this guy is going to require, plus this guy's service time, and so forth. The number of the customers he finds in front of him is q. So this is the service time of this guy, plus the service time of this guy, and so forth, added up through all q of them. Plus, when he arrived, if, and we're conditioning on the fact that he had to wait, if he had to wait when he arrived, then at the time he arrived, there must have been somebody in service. So he also had to wait for the remainder of the service time that he interrupted when he arrived. Now, that remainder is called R, and that's where the renewal theory is going to come in. Because when he arrives, either he arrives when the system is empty, in which case he doesn't wait at all, or he arrives when it's not empty. If it's not empty, then somebody's in service. And that means that he arrives in the middle of that person's service time. And that means that his waiting time includes the remaining service time that he interrupted. So there it is, and that's why renewal theory is relevant. Okay? Does that answer it? Okay. What? When he arrives, remember, we're calculating W here, given the condition that the waiting time is greater than 0. Okay? That's what we've done. We've carried that condition throughout. Okay, so that means, to continue with 8.5, what we have is this. The expected value, okay. The expected value of the waiting time, given that the waiting time is greater than 0, is equal to, okay, now we're going to take this expected value right here. So we have the expected value of the queue length, given W is greater than 0, times the expected value of the service time, which is tau, plus the expected value of R, given W is greater than 0. But now I'm going to drop the statement W greater than 0 because that's implicit in the definition of R. It doesn't matter whether W is greater than 0 or not. All that matters is that by virtue of the fact that W is greater than 0, there is an R. There's a remainder. If W were not greater than 0, then there would be no remainder. So I'm just going to write that extra piece as E of R. Okay, now let's go back and plug 8.3 into here. 8.3 says that the expected value of the queue length, given W is greater than 0 times tau, which is exactly that, is E of W. So by 8.3, this piece becomes E of W. There's my E of R. And here is my EW given W greater than 0. So this is a very remarkable result, very simple. It says that the average waiting time for those customers who have to wait is equal to the average waiting time averaged over all customers, including those who don't have to wait, plus the remainder of the interrupted service time. So it's surprising that everything works out to be as simple as that. Okay, so here's my 8.3, and here's my 8.6. And now I'm going to put 8.3 into 8.6. Okay, so I'm going to take this thing right here, and I'm going to replace this into here, so that I can solve for the conditional expected waiting time. Okay, so if I take 8.3 and put it into 8.6, then this piece is replaced by that, and I can then bring this over to the left side of the equation, and the result is the following. I get the expected value of W divided by rho is equal to EW plus ER. Okay, now let's see. Let me go back and see how I did that. Okay, according to my notes here, I want to take 8.3 and I want to put it into 8.6. So I'll replace, I can come over here, let's see. Oh, I know what I'm going to do. Okay, I'm going to take this thing right here, and I'm going to replace that piece by, I'll solve this. Okay, I'm going to take this and I'm going to solve for that. So that means that this piece is equal to that divided by lambda times tau, which is rho. Okay, so what I do is I replace this piece right here from 8.3 by EW over rho. So I have EW over rho equals EW plus ER. There it is right there. Okay, from that, I can solve for EW. Okay, so let me erase that. Okay, this implies, if I solve this for EW, I simply bring this over here and we'll multiply through by rho, either way I want to look at it. That implies that EW is equal to rho over 1 minus rho times E of R. And that's equation 810 in the text. Okay, so this equation is remarkable because it says that the expected value of the waiting time is proportional to the expected value of the remainder of the interrupted service time, if there is one. And the proportionality constant is rho over 1 minus rho, where rho is the server utilization. All right, so all we got to do is figure out what this is in order to get our answer. Okay, but now from renewal theory, we know what that is, or at least we think we know what it is. Okay, when I say know what it is, being intuitive here. Because in renewal theory, if we had a system in which the renewals were the service times, that is, the X's were the service times, and we interrupted one of those guys at random in equilibrium, then we know that the expected value would be equal to the average over 2 plus the variance over twice the average. Okay, that's this result right here. That and that. However, in our problem, we don't really have a renewal process, because what we have in our real problem is a customer arrives, and then we have a bunch of service times This customer arrives, that's when he leaves. Then some other customer arrives, let's say in here, and then he would leave here. And then some other customer arrives, maybe here, and so forth. And so you generate this so-called busy period, but then the server becomes idle. And then it becomes busy again, and you generate another busy period, and so on. Now, this would be a renewal process if I didn't have these gaps in between. However, I don't really have to worry about the gaps in between, because if we have Poisson input, then those gaps have an exponential length, and so they don't really have any effect on the future in terms of memory. So therefore, the intuition goes, I could simply imagine that those gaps are removed, and I string all the service times together. And then if I were to interrupt in that renewal process a service time at random, that would be exactly the same thing statistically as what happens in this process, in which there were gaps, but the gaps are really irrelevant. Okay, so if you believe that part, then this guy is replaced by this. That's the renewal theory, and that gives us our PolyCheck Engine formula. Now, the beauty of this argument is that it's all, although it's tricky, it's all elementary from an algebra point of view, and all it uses is elementary probability, plus it uses pasta, it uses Little's theorem, and it uses the renewal theory result. And the rest of it is just algebra and elementary probability, using things like the expected value of a compound sum and things of that nature. So it's a strictly probabilistic argument with only algebra. Of course, the reason that that it is in that sense so simple is that there's a lot of mathematics and a lot of insight that's involved in those pieces. Like there's a lot of insight in pasta, there's a lot of insight in Little's theorem, and of course there's a lot of mathematics in the renewal theory result. But if you take those pieces as elements, as units of knowledge, and you move them around, then this is what you get. Okay, now having done that and seeing how all the pieces fit together, now the question is, could I get this result by simply starting from first principles and not applying any of these theorems? I don't want to now I want to make believe that I don't understand this at all, and I don't know pasta, and I don't know Little's theorem, and I don't know anything. I'm simply going to write equations down from first principles and then follow through the mathematics, and the end result will be that I'm going to get the same result. Then what that does is that then will strengthen, it'll support the intuition and say that, yeah, the intuitive arguments that were made here apparently are correct. So what's remarkable here is that the renewal theory argument leads to the key piece. Because when you get the final answer, here's the PolyCheck Engine formula. And the PolyCheck Engine formula has in it this piece. And that piece, what you do is you recognize, this turns up all the time in queuing theory, that that piece is a forward recurrence time. And the rest of it, writing it this way, the rest of it is simply something to have to do with the utilization of the server. Now why it is, it's still not clear to me why it is that the average waiting time should be a simple multiplication of this row over 1 minus row term times this forward recurrence time. I really don't know. Of course, if you follow through the mathematics, it comes out, so it must be true, but it's still rather striking that that's the way it works. But this is characteristic of the subject, because we'll see as we get into more complicated models that we keep getting the same result over and over again. You keep getting this renewal theory result as being the central piece to these formulas. And the renewal theory result is where the behavior of the queue, where you see that the behavior of the queue depends on the variance, the distribution of the service times, and not just on their average. Okay, so the essential point here is that the sensitivity of the performance to the variability of the underlying distributions is essentially because of the bias that comes out of the renewal theory argument, or the bias that the renewal theory argument shows. And that bias, remember, is the fact that we're sampling from some kind of urn here, and we're laying these values off, and the value that we pick out tends to be longer than the ordinary value. Okay, so that effect that biasing effect, that tendency to have the service time picked out being biased towards its long side, because by exactly this argument is one of the key components of all of these formulas. Okay, now I have a homework based on this, which I think will clarify this. And it involves, well, let me just say what it involves, and I'll pass it out, and then I'll discuss this again next time. It involves a simulation. It's very simple, really, but the results are startling. Instead of simulating a queue, I'm just going to simulate the renewal theory part. So what I'm going to do is I'm going to write a program, or you're going to write a program, that is going to fix some value t, and then it's going to generate these x's by sampling from this urn. Until it gets a value in x that's interrupted by t. So let's call this value r. And of course, in the simulation, we want this t to be infinite. So that means that you have to run this thing long enough so that for all practical purposes, the initial condition is worn off. So every time you run this experiment, you're going to get a value r. And then you're going to be able to calculate the expected value, or the average value of the r's. Now I'm going to ask you to do the case in which the x's are given by a specific form, namely a constant u plus a random value y. And then what I'm going to do is I'm going to give you the distribution of the y's. Okay, now the y's are going to be, you see what I said here. Here are the y's. The y's are defined as follows. The probability that y takes the value 1 is 0.9, and the probability that y takes the value 11 is 0.1. So in other words, what you're going to do is you're going to pick from this urn values y, of which 90% of them will be 1s and 10% of them will be 11s. This works out to give you a nice expected value. I believe it turns out to be 2. And then every time you pick one out, you're going to add to it this constant value u, and then you're going to generate the x's that way until you get an r. And then what you're going to do is you're going to plot the expected value of r as a function of u. So you're going to do this for various different constant values of u. So when u is 0, as u gets bigger, as u moves from 0 to infinity, the average length of the inter-renewal times increases, but the variance doesn't, because the variance of the sum is the sum of the variances, and so if I add in a constant, that doesn't change the variance. So what I'm doing is I'm going to have a family of processes here in which the average x gets bigger and bigger, but the variance of the x remains constant. And then I want you to plot the curve that's going to result, whatever that may be. And I think that when you do it, you will be surprised. Okay? We'll discuss this next time. Actually, this is easy. I mean, it's easy to do. I think it'll just be surprising how the answer turns out, and that will have some bearing on what comes later in the course. Of course, this has nothing to do with the queue, but what we know from the lecture now is that the renewal theory is the heart of the queuing theory results. The queuing theory results just make it more complicated because they embed the renewal theory in a much more complicated model. But when you get all done, it separates out. So the key is to understand the renewal theory. Okay, so we'll start there next time.